This is part 2 to the intermolecular forces video, and this will be a continuation of the intermolecular forces that we just finished up with. And I started London dispersion forces on the last video, and so that's where we're going to pick up in this video. So London dispersion forces is a force that's real unique, and it's a little different from the dipole and ion dipole intermolecular forces we talked about in part 1. So, the PowerPoint, you can see what it says here. What I like to use a different example than what the PowerPoint slides use. And so, the example I like to use is where you take a rubber ball and you throw it into a wall. And it doesn't matter what wall that you might throw it in. It's like a brick wall. So a rubber ball, what's nice about it, it's elastic. And so when it hits the wall, it bounces back towards you. And so the shape of a rubber ball is spherical, just like an atom. And the difference is an atom has electrons spread around in its electron cloud, where a rubber ball is just the plastic that it's made up of, the polymers. So when we have that wall and that ball is coming towards it, when it hits the wall, does it stay a spherical object like it is within space? The answer is no. And so it turns into a shape that looks something like this. Now, it will compress and it'll bounce back out. But what's important here is to understand, and this is the point, is that imagine those electrons that might be floating around in the electron cloud. Once it hits the wall, these electrons are going to be shifted to the opposite side because there's going to be less space where the side it collides into the wall. And so what happens here is the electron's density is found on the other side. So as I draw it here. Now, why is that important? Because we talked about partial charges in the previous video. It forms a partial charge, and it forms a partial negative to the side that the electrons go to, and then on the opposite side, it forms that partial positive charge. Why is that important? That's important because that's where the interactions are going to take place. These partial positive and partial negative charges are called instantaneous dipoles. And so these are small dipole moments that happen, but they go away as soon as they're made. They're instantaneous. And so when we look at the helium atom, like the PowerPoint's discussing here, what happens here is you can see in the helium atom, when it collides or gets close to another molecule, those molecules or atoms are going to interact with each other because they form these partial negative and partial positive charges. So in a sense, they become polar, but only for a short moment in time. Now, once they go away from each other, they go back to their original form. Now, keep in mind that helium itself is a nonpolar substance, and so it only forms this instantaneous dipole when it gets close to another helium atom. Remember, intermolecular forces are forces that occur between two adjacent atoms. So these are interactions that are going to take place when the molecules come close enough to each other. So London dispersion forces are attractions between an instantaneous dipole and an induced dipole. So we call this an induced dipole moment. It's because it's forced on the atom. It's not something that's going to stay permanent. Again, when they go away from each other, the two atoms will return to their normal state. These forces are present in all molecules, whether they are polar or nonpolar. Where they seem to most be most prevalent are those nonpolar compounds. When we deal with polar molecules, it becomes a little bit more complex because you're dealing with dipole-dipole interactions, ion-dipole interactions, and now we're dealing with London dispersion. So London dispersion really shows up when we're dealing with more nonpolar than polar compounds. The tendency of an electron cloud to distort in this way is called polarizability. Polarizability is just the ability for an atom to polarize. So think about a pillow. If you have a small flat pillow versus a large fluffy pillow, which one's going to have more movement, more ability to go in when your head hits it, or sink in, I should say? The bigger pillow. So the bigger pillow is going to be easier to polarize than your flat pillow. And that really goes back to the size and the number of electrons that are present in those atoms. So factors that will affect London dispersion forces. Shape. Shape is important. When we look at the two different molecules on the left here, you have N-pentane and then you have neopentane. N-pentane is a long stick structure, so it's long like this, okay? When you have the neopentane is going to have a more spherical structure to it. So which one do you think would have a higher number of interactions? Well, think about surface area. Which one has a higher surface area? Pentane does. The long, skinny chain has a higher surface area. So the more surface area that you have, the stronger the interactions they're going to have. If you look at the neopentane, you're only going to have some interaction at one point because that's the only place of attraction that's going to take place. So only point of contact, I should say. So neopentane has a lower boiling point than pentane does because of that surface area that we were talking about. So surface area is a key player when we talk about London dispersion forces. So you got to pay attention to the Lewis structure again, and how big that structure is. You know, how is it flat? Is it long? Is it circular, spherical, like we see here in these two examples? The strength of the dispersion force tends to increase with increased molecular weight. This is an important detail, and this is something that is very consistent, and we can see this in this table here. So if you look at the halogens, we have fluorine, chlorine, bromine, and iodine. Of those four, which is the largest? Iodine. Iodine has a molar mass of 253.8, whereas fluorine has a molar mass of 38. And as you can see, the difference there, the bigger molecule has a higher boiling point. Now, this goes back to the polarizability that we talked about earlier. When we talk about iodine, iodine has a much larger electron cloud than the fluorine does. And so when we talk about the ability to polarize, the iodine has a little bit more cushion built into it because of that larger electron cloud. So it only makes sense that with it being able to polarize easier, it's going to have a higher boiling point as a result. We look at the noble gases, we see the same effect. We see that the larger, the heavier those molecules are, the higher the boiling point will be. So when we're dealing with intermolecular forces and we're trying to figure out whether one molecule has a higher boiling point than another molecule, one way we can do this is we can think about the molecule, we can look at the molar mass of that molecule, and we also can pay attention to the types of intermolecular forces that are present. The larger atoms are going to have larger electron clouds, which are going to be easier to polarize, and that's going to be a key player in the physical properties that you observe within that substance. So which have a greater effect, dipole, or dispersion? Because believe it or not, even though the dispersion forces only show up in everything, but they're more observant in nonpolar substances. They could be stronger than the dipole interactions. Now you got to go back to that chart in the guide where you can see the differences in the energy values it takes to break away the intermolecular forces between the two. So if two molecules of comparable size and shape, dipole is going to be the dominating force. And that's just simply a fact because it's going to have it's a polar compound, and polar substances are naturally going to have stronger intermolecular forces. However, if there's a big difference in the size, there's a slight chance that the dispersion forces will have a stronger interaction, and that's what will determine those intermolecular forces. So as we move forward, we look at this chart here and we see that there should be an increase in boiling point as the molar mass increases. The blue line shows this consistent trend, but if you look at the red line, you see an oddball. You see water. The question is why? Well, to answer this question as to why we see that, we have to focus on water and the fact that water possesses hydrogen bonding. Hydrogen bonding is the last intermolecular force that we're going to study. And hydrogen bonding is a special type of intermolecular force. It's actually grouped within the dipole-dipole interactions. But hydrogen bonding is only going to occur when a hydrogen is covalently bonded to either nitrogen, oxygen, or fluorine. Now keep in mind that nitrogen, oxygen, and fluorine are the three most electronegative elements on the periodic table, so that makes this really unique. So if I had a molecule of H2S, H2S would not have hydrogen bonding, even there is hydrogen, but it does not meet one of those three requirements, nitrogen, oxygen, or fluorine. So H2S would be a polar substance, but it only will possess dipole, and London dispersion. However, if we look at water, as you can see up here in this picture, water possesses hydrogen bonding. It is polar too, so it's polar, possesses hydrogen bonding, dipole, and London dispersion. But the hydrogen bonding is the dominant force here, and that's what keeps water together so tightly. And we talked about water droplets in part 1. It's the hydrogen bonding specifically what keeps those water droplets together. It's a strong interaction. It's a very strong. In fact, hydrogen bonding is the second strongest intermolecular force in comparison to the others that we've talked about. Iron dipole being the strongest, then hydrogen bonding, then dipole, and London dispersion. But remember, London dispersion can be stronger than your dipole. In fact, London dispersion can be almost as strong, if not stronger than hydrogen bonding, just depending on the structure. So again, the hydrogen bonding arises because of the electronegativities of those three, nitrogen, oxygen, and fluorine. Also, when hydrogen bonded to one of those very electronegative, the hydrogen nucleus is exposed. So that's where we get this interaction here. This hydrogen can interact with the oxygen from a neighbor molecule, assuming that we have that oxygen, especially within water. So now to summarize the intermolecular forces here, this is a good little flow chart diagram. You can use this diagram to sort of ask questions and try to, it just helps you in determining the type of interactions that might be present. So that's it for part 2. I might do a part 3 where we can go over specific examples. So please check back and looking for part 3. Thanks for watching.